just a couple terms in vocab, and we won't hit all of the vocab because some of the vocab we'll be using next week. So I believe this is on page 316 of your student journal. There's 4 vocabulary words, and we're going to write down vocab for normal distribution and normal curve. Does anybody else need staplers anywhere in the room? We're all good? Cool, thank you. Okay, normal distribution is just like a special set of data that has a special distribution from the mean. And what normal distribution means is that data is symmetric to the mean. Normally distributed data is symmetric to the mean. Okay. This would mean for us that 50% of our data falls above the mean and 50% of the data falls below the mean, so that it's symmetric on both sides or even on both sides. Normally distributed data can be identified on what is called the normal curve, and the normal curve is our bell-shaped curve. If you want to draw a quick sketch of what the normal curve looks like, it would look very similar to that curve in the activity we just kind of talked about with the squares. So it looks bell-shaped, has a peak in the middle, sort of comes down to the horizontal axis on both sides. And if you want, you could label right there in the middle of that curve is your mean. Remember, the book uses that fancy M, mu, for mean. Mu. Okay, so moving right along, you'll skip the next 2 vocab words, which are like standard normal distribution and z-score. We'll talk about those next week. But there's a core concept at the bottom of the page. And like this can be really hard in terms of taking notes. I do expect you to know all of this stuff, so make sure that you're like aware. If you want to star that or put a big box around that, you can add your notes to it if you want, but you are responsible for the things that are typed out there for you in the journal. So we're talking about area under a normal curve, and we're saying that we have normally distributed data, so it's important that you're told that your data is distributed normally. Not all data is. Okay. It will have a mean value, some mu, and a standard deviation sigma. Okay. So it's important to remember what those Greek letters are, because at the horizontal of your axis, you're going to see a lot of Greek symbols, and it's important to be familiar with mu as mean, sigma as standard deviation, so you can understand what each of those things is telling you. And then we know these things are certain in normal distributions. First of all, the total area underneath the curve is 1. Now that would be working if you're working with like decimal areas, or you could write 100%. So you might want to add that to your notes, that we can also say the total area under the curve is 100% of your data. The next 3 bullet points are those same bullet points that we kind of saw in that activity when we were counting the squares. Even though we were a little high or a little low on some of our counts, we were very, very close to what is actually true for normally distributed data. 68% of the area lies under 1 standard deviation of the curve, which means 68% of your data lies within 1 standard deviation of your mean. Okay. 95% of your data lies within 2 standard deviations of your mean, and 99.7% of your data lies within 3 standard deviations of the mean. So remember, there's just 0.3% of data that would be outside of the 3 standard deviations. Okay, so not very likely that we would have anybody out there.
Is that why you had us do those squares?
Mm-hmm. Yeah, to make the connections between the area under the curve and how much there is. Okay. Now, there are 2 pictures under this. And the first picture is like, I want you to think about that squares activity that we did and think about the light, the medium, the dark gray areas. Okay, it's just showing us what those percentages are underneath the curve. So within 1 standard deviation, you have your mean in the middle, and then do you see mean plus standard deviation, mean minus standard deviation, or mu plus sigma, mu minus sigma? Okay. So this is all within 1 standard deviation, and they're showing you that within the 1 standard deviation, you have 68% of your data. Okay. So the mu plus sigma and the mu minus sigma are just saying, I'm adding a standard deviation, I'm subtracting a standard deviation. Either way, I'm within 1 standard deviation of my mean, above or below. Okay. Now, pay attention to the Greek letters on the next tick marks. Okay. They're going to tell you, now you're doing the mean plus 2 standard deviations. So you already added a standard deviation. Now you're going to add another one. So this is 2 standard deviations above the mean. And then we have a mu minus 2 sigma, which is 2 standard deviations below the mean. And they're showing you that that covers 95% of the area, or 95% of your data. Okay, so those are going to be within 2 standard deviations of your mean. And the last set that they show you in terms of the Greek letters are mu plus 3 sigma and mu minus 3 sigma, which is just adding one more standard deviation, or subtracting one more standard deviation of your mean. So now we're within 3 standard deviations of the mean right here. And I'll move this up here in just a second. There is a little bit of tail beyond that mu plus 3 sigma and mu minus 3 sigma, and that little bit of tail, or that little bit of area, represents that 0.3 that is way above. Now, what I want you to look at next is that picture right next to this. And I would like you to kind of think about, and if you want to share out some ideas with the people around you, I have the same curve. I have it broken up into lots of different sections, and I have new numbers there. Can you tell where those numbers are coming from? Where did I get the numbers 34, 13.5, 2.35, and 0.15? So I'm going to give you some time to kind of play around with that. Those numbers are related to the numbers in the other picture. Okay, so see if you can figure out how we get those numbers 34, 13.5, 2.35, 0.15. Go ahead and have a quick conversation. Figure out how I got the numbers on the other graph. Where are those numbers coming from? Faith?
Well, it's 0% on those, but divided in half.
Same percents on the left side, but divided in half. So you're speaking specifically to which numbers?
It's 68%.
Like the 68%, right? 68% is supposed to be within 1 standard deviation of the mean, but that's 1 above and 1 below. So if you divide 68 by 2, then you get that 34. And so we have 34 in both sections there. So where does the 13.5 come from?
It's 95 by 2 marks.
Oh, 95 divided by 2 comes out to be 40. 46, 47.5? Which one is it? 47.5? And then you're saying minus the 34, okay? So then you get 13.5. Did anybody figure the 13.5 differently than dividing 95 in half and subtracting 34? Okay.
Well, I just said 34 plus 13.5 times 2.
Oh, so you kind of went backwards. 34 plus 13.5 is that 47.5 multiplied by 2, and then Wow, we have that 95% of our data. Okay. So I'm okay with that. Anybody else want to share anything there? Where does the number 2.35 come from?
Well, I added those together too. I did the same thing.
Okay, so you did the same thing. Now you're doing 34 plus 13.5.
I did.
Oh,
Oh, yeah. What I did was I just did 34 times 2 plus 13.5 times 2 plus 2.35 times 2.
oh, 34 times 2 plus 13.5 times 2 plus 2.35 times 2, and that came out to be
99.7.
99.7%, which is that percent we gave us. And then Faith, you could use your method, which is divide 99.7 by 2 and subtract the 2 that we already knew, 13.5 and 34. Okay, so that would work. And then what's that 0.15? It's the 0.3% that's left over that doesn't get included, right? So you have to split it in half because half of it will be above and half of it will be below because we're symmetric to the mean. But that's that 0.3 that isn't included in 99.7%. Okay, good. Okay, in that little section below where it says no notes, or sorry, it doesn't say no notes, it says notes. Where it says notes, I just want to show you how we can draw out this graph every single time, and we can use it for every single problem we do with normal distribution. Okay, so what I usually do is I start with a horizontal axis. In the middle, I put mu or x bar. Okay, whatever you want to represent the mean. And then you can always build this by adding standard deviations. So I'm going to do mu plus a standard deviation, mu plus 2 standard deviations, and mu plus 3 standard deviations. Okay, so that's easy. I just add 1, add 2, add 3 standard deviations. And then on the other side, I can subtract. So I can say mu minus 1 standard deviation, mu minus 2 standard deviations, mu minus 3 standard deviations. You've got to be okay with those Greek letters. It's just saying subtract a standard deviation, subtract another standard deviation, subtract a third standard deviation. And we're 3 standard deviations away from our mean. Then what I like to do is I always drop in my percents. So that second graph that you saw, you're responsible for knowing those numbers. 34, 13.5, 2.35, 0.15. You got to know those 4 numbers. They'll repeat on the other side because it's symmetric. 34, 13.5, 2.35, 0.15. And I'll now be able to answer any question involving the normal distribution. You can draw the curve above this if you want to. If you don't want to take up the space that the curve requires, we don't even really need the picture of the curve anymore. What we're really concerned about are these intervals. So if you flip to the next page, we've got some examples that are written first in Greek letters, okay? And I don't want you to be like super scared by these Greek letters. I'm going to flip back and forth to my last slide. You're using that thing we put in the extra notes.
Is that like an upside down N thing? Is that the same thing as the M?
Yes, that is supposed to be mu. Yes. Okay. So what we want to find here is we want a data value that is less than or equal to the mean minus 2 standard deviations. Okay, so make sense of that, what that actually means. We want to find out what's the probability that a data value in this normally distributed data set is less than the mean minus 2 standard deviations. Okay. I wouldn't normally write that down. I just want everybody to know what we're looking for. I'm going to go back to my notes area, and I'm going to search for the mean minus 2 standard deviations. Where is the mean minus 2 standard deviations? Can you spot it? Right here? Okay. And we want data values that are less than or greater than. Less than, so that would be to the left. And so what will I do with these two probabilities? Add them together. Yep, add them together. And that'll give me my answer. So I'll say 0.15 plus 2.35. The probability that a data value is less than or equal to the mean minus 2 standard deviations is 2.5%. Only 2.5% of my data falls below that line. It's kind of confusing because of the Greek letters, right? But you really just need to think about it like you're going back to that picture that we drew in the notes, and you're just going to find that boundary. So let's look at number 2. Now we want a data value that's greater than or equal to the mean minus 3 standard deviations. Okay. So your job on that slide where we have, or in the notes where we have all of the separations, is to find the mean minus 3 standard deviations. So I'm going to flip back. Can you find the mean minus 3 standard deviations? Yeah, it's real close to the last one we were at, right? Okay. So there's the mean minus 3 standard deviations. And we want things that are greater than, so we want everything to the right. How would you be able to calculate that? What are some options you could do? Okay?
You could do 50%.
Oh, okay, I agree. Like this whole piece right here is 50%, isn't it? Because it's above the mean, so 50% of our data is above the mean. And then I could just add the 34, the 13.5, and the 2.35. Okay, I totally agree with that.
You can add all of them together and multiply them by 2 except for the 0.15.
Oh, okay, so you could do like 34 plus 13.5 plus 2.35 times 2, and then add that one lonely 0.15. Okay, I like that. Anything else? Uh-huh. You could also look at the thing that is not included, which is 0.15, and then just subtract that from 100%. 100% lies underneath the curve, subtract 0.15, and that's what's left over. So any of those will work, however you want to write it. 50 plus 34 plus 13.5 plus 2.35, or Jackson said 34 times 2 plus 13.5 times 2 plus 2.35 times 2 plus a 0.15, right? Or 100 minus 0.15. And they should all come out to be 98.5%. You might choose the Hills method because it's probably the quickest, right? And so sometimes there are quicker methods than others. So that's just getting used to the Greek letters. I know that that will be weird for you at first, but remember that we wrote that nice bar out on the notes. When you're doing your homework this weekend, maybe write that real nice at the top of your paper, and then just continue to use that for all of those problems that are in the Greek letters. Okay. I'm going to skip down to number 7 so that we can do one problem that is in context. And I actually think the problems that are the word problems in this section are a little bit easier than the problems like this. Only because this throws people off with all the mu's and the sigmas. Okay, so and number 7 is at the bottom of your page. And we'll just do this one really quickly. It says, the scores for a math course test are normally distributed. Okay, that's really important. I have to be told that it's normally distributed. And then once I'm told that, I know I can use my normal curve. I know I can use my numbers 34, 13.5, 2.35, 0.15. My mean is 61, and my standard deviation is 11. So what I'm going to do, before I start answering questions A and B, I'm going to make my little chart. But I'm going to apply the numbers now. Instead of putting mu in the middle, what is mu? 61. And then I'm going to add one standard deviation at a time, 3 times. So add 11 to get 72, 83, and 94. I'm just scaling by my standard deviation. And then I'll subtract 3 times. Okay, so I'll get 50, 39, 28.
Are you just adding the numbers 34 to?
I am adding the 11.
Oh, every time.
Yep, because it should be the mean 61 plus the standard deviation 11, plus 2 standard deviations, plus 3 standard deviations. The numbers 34, 13.5, 2.35, and 0.15, they go in those same sections they belong. So those numbers are always in my problem when I talk about normally distributed data. But once you draw that, you'll be able to answer those questions on the interval. So like, what percent of students are between 72 and 83? 13.5%. And then you just add the percents. I'll post the notes online and the video, and then there's your assignment for the weekend.
That'll be on the website?
Yep.
Okay.